First, I also would like to thank the organizer give me this opportunity to present the star measurement for the small system flow. Okay. Let's talk about something about the system evolution in a small system. Not like the large system, the evolution in a small system is quite complicated. First, we know the initial spatial geometry is not easy to calculate. We have some different model, like a standard nuclear globe model with a subnuclear globe model, which will give us a different answer. Also, if the hydro start as a tau 0 plus, we expected the flow will be proportional to initial eccentricity. Well, in the framework like IT plasma plus hydro, the star is like tau equal to around 0.4 for me over C, then we expect the very large initial state contribution, like the initial momentum correlation, the pre-flow from the IT plasma. Furthermore, in the recently development from the Shen group, they use a 3D dynamic globe model that the hydro will start at a different time and a different regime that make the whole system even more complicated. So the weather star measurement can help us understanding this. I think since it's extremely complicated, the picture, so I think we don't impact the one measurement can resolve everything, but I hope the star new published measurement can shed some light to help understanding this and give us some guidance to resolve all of them in the future. So first, I just give it a little bit more detail about the initial spatial initial geometry in a small system. We know there's two kinds of the globe model calculation. First, it's just like a standard globe model without any flow Coulomb field fluctuation. You can see there's very strong system dependence. You see the Highland-Segal and Deagle have very large eccentricity compared with the Peagle, and for the Highland-Segal, we have very large eccentricity compared to the Deagle and the Peagle. Well, if we include the Coulomb fluctuation, this system dependence simply disappeared. The three system, the eccentricity looks pretty similar. So therefore, to measure the flow in these three systems will help understanding which way is more appropriate to calculate the eccentricity in a small system. We also can look at the sonic model calculation. That's like more like a standard hydro calculations. You can see from the sonic model, the V2 and the V3 ratio is shown in the left and the right pan respectively. The red one is the V2 ratio for the Highland-Segal to the Deagle, and the blue one is the Peagle to Deagle. You can see for the V3, the Vn ratio is roughly held proportional to the V3. That's as we expected. But the V2, you see the little bit deviations around like 20%. That could be due to some maybe different with cost correction or something else, which we need to further understand. But in general, we see if in the standard hydro calculation, looks like the Vn still proportional to N, that still works. Right? That means if we can measure the flow in the three system, we can understand how the eccentricity in the small system between these three systems. Now we start talking about the measurement. In the star, we measure the two-part correlation with the mid rapidity, and in the program measurement, like on the Phoenix, they measure like a backward and the middle rapidity. So I just say which one is better, what is the advantage and what is the disadvantage for these two kind of measurement. First, you can see this is the Phoenix published the DN distribution in the Highland-Segal, Deagle, Peagle compared to PP collisions. You will see in the PP collisions, we know in the forward rapidity, the multiplicity is dropped. It's dropped in the forward rapidity, but in the asymmetric collisions like Peagle, Deagle, Highland-Segal, you see the very strong significant enhancement. That already tell us the situation of the like a Pico to Helium cycle is not like a simple superimposed PP, right? First, most of the non-flow estimation, we just assume that this the Helium cycle to Pico is a simple superimposed PP, but the multiplicity already not the such story. So if we measure the backward and the midward rapidity, so that will face some difficulty to do the non-flow subtraction. Well, if you measure the two particles both in the mid rapidity, the things will looks like a little bit easy compared to measure the mid rapidity and the backward rapidity correlation. But the disadvantage is if we measure two particles both in the mid rapidity, then the rapidity gap will be relatively small, right? That's people were expected the non-flow suppression will be the power will become weak. We run some hiding simulation, compare the different eta gap we used. One is like a red one is more like we use in the mid rapidity, and the blue one is more like the mid and the backward rapidity. You could say for the V2, you do say that if we make the rapidity gap become larger, then the non-flow will be further surprised, right? That's expected. But for the V3, you see this does not have much. It's almost similar. That's always tell us this the eta gap does not have much for the V3 measurement. And furthermore, we know there's a very large the longitudinal decorrelation in the two-party correlation measurement. This is the decorrelation measurement in the LGC and the RIC. You see, there's a very large decorrelation and the low multiplicity. For the asymmetric system like a P-LIDE is much larger than the lead-LIDE asymmetric system. Also in the high energy, the decorrelation is smaller than the lower energy. And for the third order flow, the decorrelation is much larger than the second order flow. So that means if you measure the asymmetric system like Pico, Digo, Helium cycle, and the RIC energy, you will face very significantly decorrelation. Right. Sorry,
what is FN? What is plotted here?
Oh, this is sorry. I should put the definition. This is the FN is measured this is measured VNN between the reference between the reference and the particle which is interesting as a function of delta eta. This is like more like a slope. Yeah. So when you have a large slope, that means your VN will drop significantly when your eta gap become larger. So that means your decorrelation will become larger. Yeah. So now we can see, right, to measure the two particles both on the mid rapidity have a lot of advantage to avoid the decorrelation, and we also can properly surprise the non-flow and also estimate the non-flow to do the subtraction. So STAR measured the two-particle correlation with the two particle measured in the TBC and the mid rapidity, and we also do the measurement with two kinds of centrality. One, we use the centrality, the multiplicity with the same rapidity as a particle to do the 2P correlation. We also use the BBC, that is in the backward rapidity, so we can avoid the autocorrelations. Now I just show you the STAR measurement for the two-part correlation and the mid rapidity. First, I just show you the two-part correlation measured in the Helium cycle, central Helium cycle, Digo, and the ultra central Pico collision, and compare with the PP. You can see in the PP we do not see any near side peak, but we do see a clear near side peak from the Pico to the Helium cycle collisions. That already indicate there's some flow signal in the central Digo to Helium cycle collisions. But we also say that there's some non-flow from the stronger away side the peak from PP that which needed to be removed. So we use four kind of the well-developed method. The first three method is it come from the Fourier fit to the from the two-part correlation. First, we call it the C0 method. That formula is shown like this way. In general, we use PP as a reference, then diluted by the difference of the multiplicity. Then we can subtract this as a non-flow. The second is since there could be some jet enhancement in the central pGo and to helical collisions compared to the PP. To avoid such enhancement, we use the near side jet yield to do the scaling. So that can further do some correction to the non-flow subtractions. The third method, we just assume the away side, the jet is the non-flow is dominated by the C1 component. So we just use the C1 component to do the dilution to do the non-flow subtractions. We also use the template fit that is come from the Atlas collaboration. The details you can see from the reference. In general, we found this method gave us very similar results as the C1 method. So we have the four kind of the non-flow subtraction, then we can compare the results. So you can see the left plot show you the V2 results as on PT in the 3 system, and the right is V3 from the four kind of method, and also compare with the results before the subtraction. First, you can see the four method give us pretty similar results, right? Except that the P2 have a little bit span due to the non-flow uncertainty, but we stand this difference as a systematic uncertainties. And you can compare with the results before the subtraction. You can see the non-flow gave the positive contribution. So after subtraction, the results will become lower, but the non-flow gave the negative contribution. So the subtracted V3 will be larger compared with the V3 without the subtraction. That is also we expected. Then we further to the delta eta gap from 0.8 to 1.4 because we know the jet waves from the pGo to DGo collisions could be a little bit different to the PP. So we are tuning this the delta eta gap to avoid these uncertainties. So in general, you can see after the subtraction, this is for all the V2 results from 3 systems with a different eta gap. You can see after subtraction, all the results are consistent, whatever eta gap we use. Also, the same story for the V3, you can see before the subtraction, you see once we have the large eta gap, the V3 a little bit smaller, but after the subtraction, all the results are also become consistent. That's indicate the non-flow is well handled in the STAR collaboration. We not only measure the V2, V3 with the TPC centrality, we also measure do the same measurement with the BBC centrality. As I already mentioned before, because there's a rapidity is in a different regime, so we can avoid the autocorrelations. You can see the two kind of results are consistent with each other whenever centrality was selected. Now we can make the comparison to the Phoenix, which has been done a couple years ago. So you can see here. First, we compare the V2, V3 in the helical system. You can see the both V2 and V3 are pretty consistent in between the two kind of between two collaboration. And also for the V2 in the DGo and pGo collisions are also roughly consistent between the systematic uncertainty, except maybe 25% difference. But unfortunately, we see significant difference for the V3 in the PIGO and the DIGO collisions. You can see the detailed comparison here. Roughly difference the factor 3 is significantly and cannot covered by the systematic uncertainties. As already mentioned, there could be some decorrelation in the physics measurement due to the two particle is from the backward and the middle rapidity. Recently, there's some calculation from 3D global come from the Wenxing and Shen's group. You can see this the blue line is the 3D global calculation with a Phoenix method, and the pink line is the from star method. I want to point out this for the V3 in the PIGO and DIGO. You see there's a significant difference. That's a decorrelation will make the V3 significantly smaller. But they still underestimated the star measurement, right? Right. I think the models simply need some improvement in the future, like they could some other effect like a pre-flow or some non-flow in the calculation, which can be implemented in the future. Because in this one, you can see in the PIGO collisions, if the model added the pre-flow effect, then make the both V2 and V3 become bigger and more close to the star data. Right? And we also know this pre-flow could be different for the different system. So I think in future, we would like to package it to the calculation from the DIGO and Harness circle to make sure the pre-flow could make the new calculation more consistent to the star results. To further resolve this puzzle, right? We take the new data in 2 years ago, 2021. This is a projection which we the projection from the 100 million data we already taken. So you can see with this 100 million data, we can do the very good measurement in the both Phoenix method and the star method. So we can, in the same collaboration, we can repeat these results to further understanding the decorrelation and some other issue. I want to point out this data taken is no any beam cross angle, right? Because the Phoenix results it come from a very large beam cross angle. They claim they will affect their even plane resolution. But the new data we taken, we have no any beam cross angle, so will be more decent then should we say more easy way to understanding the difference. Okay, the further we can compare the star measurement with other the model calculation. First, we can compare the IT Glasma plus Hydro. Right? We know the IT Glasma in the initial stage have the some initial moment correlation and the pre-flow. Right? So, but unfortunately, this model is tuning with the larger system and extrapolate to the small system. It would be better. We can say before the tuning, right, like use Harness circle the tuning to see how the calculation will look like. In general, you can see the model calculation over predict the V2, right? But describe the star V3 measurement quite distantly. Right? So for this over prediction of the V2, that could be due to the they have the very stronger pre-flow effector. They also maybe due to they have very larger eccentricity 2 compared with the eccentricity 3 in the model calculation. Right? Also with compared with other models. Yeah, we also further compare the star measurement with the sonic model calculation. You can see the sonic model can describe the star V2 results, but underestimated the V3, especially in the DIGO and the PIGO collision is more than factor 2 underestimate. Right? We want to point out that their eccentricity used in the sonic model is very small. So that may be the one of the reason the sonic model underestimated the V3. So if we use like eccentricity from the subnuclear fluctuation, you can see their eccentricity will become significantly bigger and also will be similar. So I think in the future, I think we packed some calculation from hydro export with subnuclear eccentricity plus the hydro to see whether they can reproduce both V2 and V3. Okay, then now we can further to compare the system to do the system dependence. We compare the V2 and V3 in the three system with a similar multiplicity. We select the centrally bin, make the multiplicity are pretty similar each other. Since we know the final state in contribution will be largely cancelled out due to the similar multiplicity. So such a ratio will help us to understand the spatial geometry and the contribution from the initial stages, since the final state will be expected to be cancelled. Right. From this ratio, we can see the V2 between the hydrogen signal and DGO is pretty similar, but both are higher than the PGO results. It's around like 30% higher than the PGO. For the V3, we see all the system, three systems have the similar V3. Now we can compare with two baseline, right? We use the eccentricity ratio from the nuclear global model and the subnuclear model as a baseline to compare the star measurement. You can see if we use the subnuclear global model, the ratio is pretty similar to the star measurement. But if we use the nuclear spatial global model, the results is much higher than the star measurement. That almost rule out this the initial geometry if there's no any contribution from the initial stage. Right. So I think looks to me the simple picture is to just have the subnuclear geometry plus hydro could be easily explain the star measurement, or we need some very complicated initial stage contribution. That's what we need to be handled. Right? I think so far that is we can learn from the star measurement.
So when you see initial state contribution, what do you mean?
It could be some pre-flow, some like initial moment correlation, something else. Yeah. Yeah, because we know the pre-flow also will change, right? So yeah, if we, just like the epiplasma plus hydro, they have some like a very strong pre-flow effect. Will affect the initial geometry.
Yeah, that is always the issue, right? I mean, those are if they are model parameters, like for example, the pre-flow, they sort of like you put in by hand, they become a fitting parameter. It will, at some point, it becomes very difficult to constrain using the data.
Yeah, so yeah, that generally we don't have that's now I say simply we can explain data with either way, right? But if we go to the complicated picture, then we need to be careful. I think maybe we need a further measurement to constrain it, right? So yeah, I don't say this is no pre-flow. Right? There could be some pre-flow. It's also very exciting the picture, but we need I think we need some other measurement to further pin down whether there it is or not. Yeah.
Epiplasma pre-flow is not a free parameter. Yes,
but is this the same as the momentum anisotropy, or this is separate from?
Well, it has an anisotropy, but it also has an average transfer flow.
Yeah, but you have this upper parameter which you can change from 1.5 to 0.15. I mean, what Shami showed in earlier.
It's not actually
that's different, yeah. Different. Okay. That's from 3D global. That's the trim put by hand.
Yeah, so, then why you got this? So they are all momentum anisotropy, initial momentum anisotropy.
Well, this one, I believe, is anti-control.
So, Shangley, you have 5 minutes left.
Okay, yeah, no, I have I have one more slide, so don't worry about it. Yeah.
All right, good. Plenty of discussion.
Yeah, if you want to keep discussion, I just one more slide left, so I can. Okay, yeah. So then we also take the outsourcing data in 2021. That's really good. We have the take the different the trigger. You can see we have the more central trigger with the 12, that is the mid rapidity. Also the high trigger with the EPD, that's backward rapidity. So that can give us a different centrality selection. Right. We also take quite a lot of data, the 400 millibytes and plus 200 million high master events. So with this very good data set, we expect we can measure the flow in the outsourcing. That is a symmetric system that could be very different with asymmetric system like a P-Go to Go. That could help us further understanding the system evolution in a small system. To say whether there's some nuclearization and some like a pre-flow like this contribution from the initial state. Okay, I think that's all. That is a summary. I don't want to read it again. So if you have a question, so yeah, you can ask. Yeah.
Listening. Questions? Yes, yeah, Junior.
Go to slide 22. So there are maybe the two questions. The first one is for discussion. Actually, I want to know when you have a pre-flow. I'm naively understanding your mean P increases, but why the VN also increase? In general, they always increase. So if you run pre-flow all the way to the end, you won't have any VN, right? Right. But then if you only run the pre-flow up to some point, then your VN actually increase.
No, they just develop faster.
So the response to the initial, initial spatial eccentricity becomes stronger if you turn on the flow later.
Well, if you have some,
If you let it happen by freeze.
No. I think alpha pre-flow larger doesn't mean the hydro starts later. The hydro always starts immediately, right? This is the streaming model.
At that time, we already have some flow already flowing.
Okay. Okay, so in this calculation, the pre-flow is actually hydrodynamics. Or not?
No, these are just like a free streaming.
You just put an initial, like at the time it starts, but it's already there.
So the free flow is not dynamically evolved, it's put in by hand.
Yeah.
It has an isotropic flow.
So this is not a time, right? It's not how much. It's like a, what is it, like a boost, I don't know, parameter. I don't know.
But these parameters can be tuned.
Yeah.
But I don't know.
But when you do pre-flow, for example, from a free streaming model, it's sensitive to the geometry. And so there is not just a radial, but also an anisotropic pre-flow that exists at the point where hydrodynamics starts. On the other hand, at the same time, the eccentricities have changed. So the geometric distribution has changed. And these effects partially compensate each other. So it's really a question of how fast the flow develops in hydro versus non-hydrodynamic pre-hydrodynamic stages.
If there's no interaction, you won't have any response to geometry. If you let it be free streaming, there's no.
I mean, but you impose an interaction when you do the magic of hydrodynamics.
Okay. So it's a sudden.
There is space momentum correlation between when you manipulate it hydrodynamically manifests immediately after low.
Okay, but this is a big action.
I have a question.
Yeah.
Could you please show the slide number 10? Yes. Here you have helium, deuterium, and proton. Are you planning to look at the heavier nucleus scattering goals? Because tendency is such that you increase the atomic weight of the particle, the incoming particle, and the forward and backward becomes more, forward becomes more suppressed. Right? Are you planning to do heavier nucleus instead of helium-3 something else?
You mean the high flavor particles?
Oh, heavy nucleus.
Heavy nucleus. Okay. Yeah, for current data set, I think in the oxygen we may can try the data is much more better.
Expect at some point the backward and forward to be equal or something like that, depending on atomic number of incoming particle, incoming nucleus.
Yes,
Yes,
sorry, I'm not fully understanding your question. In fact,
So on the right plot, you show proton on gold,
Mhm.
right? So forward and backwards are very different. Then you go to the very left, and you see they are more close to each other, peaks. What if you go to heavier nucleus incoming? It will be equal, or what will happen? Or you are just so confident you don't want to even look at that? What is the reason? You are not looking on heavier one.
So they've done gold, it's like hyper gold,
Gold,
the heavier
Yeah,
you,
yeah.
sure, they've done gold all the time. And it becomes very symmetric.
Yeah.
Yeah, in fact, so we started with gold and like copper gold and then,
Gold will be lost.
and then, yeah, and then went to smaller systems.
Yeah, because you have when the multiplicity become lower, you have like a very C1 component due to the momentum conservation, right? That make the away side peak higher, right? If you go to the gold, the multiplicity higher, this one be much diluted. Then you will see the two peak more symmetric. In fact.
But I think if I can go back to the original question I have is, there are multiple components in the early stage, other than the eccentricity.
Which is
Yeah, I mean, just a comment, because you said, okay, I mean, there's other sources other than initial eccentricity, right?
Mhm.
At some point, it's very difficult to constrain them because that depends on the model detail and you can compensate each other. You can compensate the hydrodynamics by how much anisotropy you put in the initial stage. How can we experimentally constrain this? We can measure all these different species. It's very, I mean, to me, is how can we do that? If it's always you can always put in some free flow. I mean, you don't do it, but the other people does it. How can we distinguish initial momentum anisotropy from the hydrodynamization part, for example?
That's very difficult.
Yeah.
And so you will not be able to do that with our models. And for example, as we just discussed, free streaming followed by hydro is a crutch. It's not a model. It's very artificial.
But the initial momentum anisotropy doesn't really survive unless you go down to very low multiplicity.
You said they don't play a role in all this.
If in the 0 to 5% ones there, I don't think they play much role. Maybe but not that we.
Okay.
I would also argue we need to look at more than just the two particle correlation, right? I mean, you're just looking at V2, V3 here. One should really look at like V2,4, V2,3,4, symmetric cumulus. I mean, there's a whole host of observables that one should calculate.
That's what you have to count on. That you can describe everything simultaneously at some point, which is not the case. I think.
Yeah.
Okay. Yeah.